Okay, so today, this is our last section within the chapter. We're going to be talking about, doing composition. A composition of writing is where you put a bunch of words together or sentences to make either a narrative or to make a poem, or a composition musically is to put a bunch of notes together, musical instruments together, etc., and to make a symphony or something like that. And so we're just going to be doing multiple transformations in a row. And so a composition of transformations results in multiple transformations. And so you start with an original shape, a pre-image. Okay. And I think the biggest thing that kids struggle with is you start with your pre-image. Okay. Start with that. And again, you're like, why would they struggle with that? Well, you start with that. And then what you do is you do one transformation to that shape. Okay. And so if your first transformation is to reflect it, you can imagine this would be the resultant shape right here. Okay. Well, instead of going back to the original, okay, and be like, let's do no problem. Well, no, that was like so last section. We're like, let's do multiple problems. We're like, do this transformation. Okay, cool. Now we're done. Try a new problem. Now we're gonna say, pardon me. Instead of starting over, we're going to take that result and then we're going to do another transformation to that. Okay. And so it's like, okay, now let's scooch it. Do you see this is a line of reflection here? So we've reflected across that line. Okay. And then if you see a ray, you know that's a vector. A vector says scooch your shape this direction, kind of up and to the right, this length. And so you need to use some patty paper. Remember, you trace your this new pre-image, okay, temporary pre-image, and you trace this. And what you do is you scooch it in the direction of that until, okay, the end of your vector matches this. Okay, so you scooch it on the patty paper, copy both of those green things, scooch it north, okay, and then my pen is not working. Bother, it makes me really cranky. And then here it is until it matches here. And then you redeposit the shape. You'll have to have made marks on the bottom of your shape so that when you mark from the top, it redeposits those points as your double prime or your final result. So the pre-image doesn't have any prime. Your first transformation has one prime. Your second image is going to have a double prime. So you can do as many transformations as you like. And if you do isometric transformations like translations, reflections, and rotations, your resultant images will be congruent. Okay. And you just mark them with those primes as they say. Okay. So step one was we reflected it. If I can write, that'd be good. Let's say reflect across line L. Okay. And then the second step was going to be translate. And we would use vector V. Okay, which told us, hey, go this way, this far. Okay. And so a composition of two or more isometries is also isometry. That just means they're congruent. Okay. Multiple isometric transformations form an image which will be congruent to the pre-image. Okay. Now, the thing is we can do this and it'll be kind of crafty and fun. But there also is some logic to how you can do, sometimes you can, if you're going to go someplace, sometimes you can take two big steps to get across the room, or you could take maybe two or three smaller steps, okay, to get across that, okay, or three or four smaller steps to get across that. And so what we're going to do is like, okay, so let's start with a shape. And let's reflect it a couple times and see what you get. And then guess what? If I had slid it, you would get the same result. You're like, well, that's exciting, and so you can say, how could I get the same result doing two different things? And so, and we're going to talk about two different instances where you can do it one way or the other, and either way you get the same result, and talk about what we notice. Okay, so the first one is called the reflection across parallel lines theorem. Okay, if you've ever cut down a tree and you're trying to get the big huge stumps across your yard, you probably flip them end over end, as you're trying to, or maybe you roll it. Okay. But might flip them end over end and you could get them, or you could have drug them across the yard. Well, I'm not going to drag a big stump across my yard. I might flip it end over end. So, reflecting it a couple times might be easier than dragging it. Okay. And so that if that doesn't make sense, I can show you visually, but I think the main thing is I can reflect a shape twice and it's the same as if I had slid it across the paper. So let's look at this first example. Okay, here we go. So starting with this pre-image point right here. Okay, again, pen not working. Awesome. There we go. Start with this. If I reflect it, I get this green one here. And then if I reflect it across this line here, I'm going to get this red shape, okay, on the right. So reflecting across these lines, again, it's going to be equidistant from the line of reflection. That's why this red jump is so much further, okay, because it's kind of far from the red line or from the second line of reflection. So therefore, your second reflection is going to go further than the first one, okay? Your first shape is closer. And so the math of this is, if you have a translation, you could have accomplished the same thing by reflecting it across parallel lines to get there. Okay. And the math of it also is that, and let's read this fine print. So part of this theorem says that, I'll scooch up my paper. The translation vector, what's that mean? The one that scooches it. Remember, the vector is this thing right here. Okay. The translation vector that takes it from here over here is going to be perpendicular to those lines of reflection. Okay, so you see, yeah, it is perpendicular to the lines of reflection. It's right here, both of them. Okay, so that's true. And I can't make a right angle on the other one. So you can trust that she's there. Okay, there she is. And then also another mathematical instance that you could say, oh, I noticed this too, is that the length of that translation vector, okay, so the overall length of it is equal to 2 times the distance between the lines of reflection. So if you look at the distance between these lines of reflection and say that's x, can't write an x. Awesome. I kind of wrote half one. That means the overall arrow from here to here is actually 2x, okay? So it's twice as long, the vector of translation. Okay, so again, the math of it is something that we should note. Okay, I did one from my other class on a coordinate plane to be like, hey, look at, even if you had a square on a coordinate grid and you reflected it twice, once across a line and then another across another line of reflection, you could have just slid it. Okay, and again, the distance between these two lines, x, is equal to 2 times it will be the overall distance of this vector. Okay, that would be 2x. So I kind of created that from something I found online. And so I'm not going to ask you to do that. I'm just telling you it does work on coordinate plane. It does work in space. And so just noting the features of the translation and the lines of reflection are going to be perpendicular. And then that distance between them is equal to 2 of the, you're going to double it to get the length of the vector. Okay. And then looking at another composition that's kind of special is this. If you want to talk about a rotation, any rotation that you do, you can actually have accomplished it by reflecting across intersecting lines. Okay, so it's weird that the point of rotation right here, if those 2 lines of reflection are going to go through that point. Okay, and so if you reflect a shape twice, okay, over those 2 lines, it's as if you had rotated through space. And so the things to notice about this theorem would be the center of rotation is the intersection of those 2 lines of reflection. That's the first thing, okay? And then secondly, the angle of rotation is twice the measure of the angle formed by the lines of reflection. So again, we're doubling, okay, the distance between those 2 lines. So if this angle is x degrees, the overall angle that you rotated this is going to be 2x degrees. Okay, so how far did you move those shapes? Double that degree. So if you measure this angle using a protractor here, if you double it, you're going to get the overall rotation that you did. Okay, and so I did map this out on a coordinate plane just so you could see it. So if this is your pre-image right here, and you reflect it across the y-axis and then the x-axis. Again, the angle there is 90 degrees. It's as if you rotated that you stuck this on a stick and you rotate it through space 180 degrees. Okay, so and you can also emulate every one point too, to say, if I take a point and I rotate it 180 degrees, remember that's opposite of x and y. If you take a point and you reflect it across the x-axis, which changes the x and keeps y the same, you take that point and you reflect across, oh, actually across the y, who does this, sorry. And then you reflect across the x, reflected across the x changes the sign of the y. You're going to end up with the same resultant point. Okay, so again, I'm not going to make you prove that, show that, but we're talking about composition of transformations and saying, if I do two reflections, one either across parallel lines or across intersecting lines, what happens? If you do it across intersecting lines, you get a rotation which would be equal to it, and then or comparable to it. And then, or if you reflect it across two parallel lines, it'd be as if you did a translation. Okay, so those are interchangeable of sorts. We're just talking about options and just what we notice. This one here, I'm going to actually have you guys use dot paper and just practice saying, hey, if this is my pre-image here, can you practice, reflecting this twice across parallel lines, and the resultant image is going to be as if you had just slid the pre-image horizontally. Okay, so let's do this. And this is not necessarily common, we're just kind of showing it, doing it, looking at it, our own cute self. So to reflect it, we can just count dots, okay? Remember, when you reflect, your pre-image and your image distance are going to be equidistant from that line of reflection. So if you want to do this point B, it's just basically 2 hops from the line of reflection. So let's do 2 hops. And that would be our B prime. And then, so that's the top of our shape. And then if you want to do this one down here, it's basically 2 steps from the line. And so here it is. This is going to be, I don't know, I can't read what letter that says. And then this one is going to be 1, 2, 3, 4, 5 steps from the middle. So let's do 1, 2, 3, 4, 5. And then we are going to have this is our first image. Okay, so pre-image is here. Our image is there. I'm going to color her in to make her kind of cute. All right. This is not the cutest of colors, but I'll pick a color. Let's do yellow for south. Okay, so here we go. And then let's reflect it across another axis, okay, or another line of reflection. So here we go. When we do this again, it's got to be equidistant from this line of reflection. So it's going to be 2 steps over. And this one is a lot. So it's 1, 2, 3, 4, 5. So let's count 1, 2, 3, 4, 5. This one is 1, 2, 3, 4, 5. 2. Okay. And this last one is 1, 2, 5, 6, 7. Okay. If we counted right, it should be congruent to our original pre-image and just look like a slide. Okay, and so I'm going to color this cute thing too. Say, okay, here is our double prime point. So if you were labeling these points, you would call them double prime. Okay, and notice we've got this right here, A, B, C, D, and those are all double prime. And let's see, I'm going to zoom in a little bit so we can look at these guys here. Oh yeah, they do have points. Okay, so let's look at this. So this would be D prime, because notice they're equidistant. This would be C prime, B prime, and this is probably A prime if this is A. And then as you reflect it one more time, this is C prime. This would be C double prime. This would be D double prime. This would be A double prime, and this would be B double prime. Okay, so you can reflect it twice across parallel lines, and that's the same as you translate it, double the dimension of the distance between those lines. So let's see if that's true. Okay, first of all, how far do we shift a point? Okay, so we can count how far did you shift point D. Okay, so if we count this, we could be like, okay, I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 points. Okay, so we went left 14 points. Okay, and we didn't go up any. Okay, so if we want to write as a vector, we went left 14, but up nothing. Now, we know the overall distance that it shifted by this vector, okay, is going to be left 14. Okay, I put alpha left in. It should be twice the distance between these lines of reflection. So let's check it. 1, 2, 3, 5, 6, 7. So these are 7 apart. So that means it does make sense. Okay, so if you do a reflection across parallel lines, the distance between the parallel lines is how far, twice the distance of that will be how far the shape actually shifts. Okay, so let's go and talk about reflecting across intersecting lines. Okay, and so if we reflect this same shape ABCD across two intersecting lines, it's going to be like we did a rotation. And so if you see this angle is 90 degrees, well, it's going to be like we rotated 180 degrees because it's you double the angle between those to get the angle that it actually rotated. So this one here, if you need to use, I think we're going to use patty paper for this one. So I would say take out your patty paper and trace the shape, okay? And you're going to also draw this line here, okay? When you reflect it, okay, so you're going to draw this here on top of your tracing paper. You're going to reflect it on its stomach, and I'm going to try to eyeball it, but it's not going to go well. When you flip it over this shape, it's going to give you a reflection over here, okay? So these would be, if this is A, this would be A prime, this would be B prime. If this says D, it's D prime, and this is C prime. Okay, if this is C here. And then we're like, okay, let's reflect it again. Well, then draw this line here. And so as long as you've drawn on top of this, okay, so draw on top of this, reflect it across this other axis. So flip it over its stomach, realign this line of reflection, and you're going to get this graph over here. Again, I'm eyeballing it, so it's not going to be perfect. Sorry. I can't use tracing paper very well on this. And so if you draw a line from here to the center and then a segment from here to the common point, you'll notice we did go 180 degrees. Okay, so we'll use tracing paper to make that a little bit cuter. Okay, and so the single transformation would be to rotate 180 degrees. Okay, so here's another example of like, can you draw those lines? Well, if this is our center of rotation, we know they need to intersect there, right? And if you measure like the angle between L's, okay, it should be half that size, okay? That would be the degree between these. So I'm going to just kind of eyeball it a little bit and just say, if I draw this, you know, it's got to go through here. If I draw this like this, if you reflected it once, then this graph would go like here. And if you reflect it again, it would go into the red shape, okay? So, again, this angle here, if you double it, you're going to get the actual angle that it rotated. And if it rotates, remember our lines have to intersect. So that's just kind of us eyeballing and say, how can you actually make that happen? Where it looks like if you reflect it twice, and you could use your patty paper to check it. Using those lines as lines of reflection, a rotation is equivalent to two reflections across intersecting lines. Okay. Where that point of rotation is where the two lines intersect. Okay. Hey, we're getting better. The next thing we'll do is say, okay, this is what I'm going to actually ask you to do. Okay. Can you do multiple transformations to this shape? Okay. So read what it says. There's the pre-image ED or DEF. Okay. And they say step 1. Okay. Okay, they say, let's do this glide reflection. So we're going to glide. Gliding is translating, okay, and then we're going to reflect. So first we translate, scooch, and then we reflect, okay? And so it says, translate along u, the vector u. So that means scooch it to the right, the length of vector u. Okay, so it says scooch horizontally and count the length of this. So the length is 1, 2, 3, 4, 5, 6, 7. What I'm counting are the boxes below this vector. Okay, do you see there are these boxes there? So I'm just counting the open spaces there. I'm going to scooch it 1, 2, 3, 4, 5, 6, 7 steps to the right, 7 right. Okay, so every point has to go 7 points to the right. I normally start with the one that's not behind a figure, like the starting point. Like this one here, if I count, I'm not going to be underneath the shape. So I can count 7 easy. So 1, 2, 3, 4, 5, 6, 7. And so this would be F prime. Okay, another easy one to count would be D. So just go 1, 2, 3, 4, 5, 6, 7. And this would be D prime. Well, we know it's going to be congruent, so you can just drop this E prime below it. Okay, so that's going to be our first step. Scooch every point. Yeah, we scooch every point 7 to the right, just because that's what the vector said. Go right, 7 hops. The second step says reflect it across the line L. Okay, well, we can reflect it across that line of reflection. And so again, when we reflect things, they have to be equidistant from that line. So point E is going to be, it's 1 point above the line, so it's going to be 1 point below it. So that would be E double prime. F is 1 point above, so that's going to be 1 point below F double prime. So this is going to be the start of it. And you're like, okay, what's it going to look like? Well, you can count how far D is from the center, from the line of reflection. So that's going to be 1, 2, 3, 4. So from the center, it's going to be 1, 2, 3, 4. Also, you can say, how tall is the shape? It's 3 cubes high. Okay, make it 3 cubes high. Again, it has to be congruent to the pre-image. And so this would be D double prime. Okay, so we did a translation, and that translation said go right 7, and the reflection across the line, line of reflection. Okay. We've got 2 more we're going to do. The first one's pretty cute because it doesn't overlap. The second one has some overlapping, which in my opinion is not as fun. Okay, so here you go. We're going to take our original shape, which is going to be 1, -1. That's G. H is 3, 1. And J, which is 3, -2. So we got ourselves a triangle. I should probably erase my G and move it outside the figure because it's kind of ugly there. Okay. I can't erase it very well, but we'll just go with G is here. Okay. So what they want us to do is those 3 points is they want to reflect it across the line y equals x. Okay. So we'll take each of these points and we'll reflect it across y equals x. I'm going to write that down. Reflect across y equals x. And the formula for that is you interchange x and y. So you put y and then x for every point. So our G prime point is going to be -1 and then 1. Our H prime point is going to be 1, 3. You're just exchanging x and y. And then our J prime point is going to be -2, 3. Okay, so we can graph these. I'm going to make them green. I'm going to try to color code your stuff if you want to. -1, 1. So that's G prime. And then H prime is going to be 1, 3. And then J prime is -2, 3. J prime. Okay, so we got our triangle. And it reflected across the line y equals x. Well, where's the line y equals x? Well, the line y equals x is the line in which every point is the same. So 2, 2, 3, 3, 0, 0, 1, 1, 5, 5. Okay. And -1, -1, -2, -2, etc. So it does look like reflected across the line y equals x. Awesome. And then it says take those points. Again, my mistake that I've had lots of kids do until they learn better is to take these points and then we're going to translate those. You don't go back to the original. This is not a new problem. You're saying from that new location, we're going to reflect across the x-axis. Okay, how do you do that? What we're going to do, the formula is going to be keep x the same and the y will be opposite. Okay, and so to do G double prime, okay, you're going to keep X the same, and you're going to make Y the opposite. To do H prime, you're going to keep X the same, and Y will become opposite. And J double prime is going to be keep X the same, and Y will become opposite. I'm going to get a new color. Okay, and then we're going to do -1, -1. Okay, that's going to be G double prime. And then we're going to do 1, -3, 1, 2, 3 down here. That's going to be H double prime. And then -2, -3 is going to be J double prime. And so if you draw that triangle, that is going to be the result of you reflecting that green triangle across the x-axis. And it looks true, doesn't it? Okay. And so we did it. So this would be the resultant image of two transformations. Okay. Two reflections. Okay. The next thing we're going to do is we're going to look at this one here. That's going to be a quadrilateral. It's going to overlap a smidge. So just breathe. It's going to be okay. So step one is we're going to graph it. And so A is going to be 1, 1. B is going to be 2, 2. C is 5, 4. And D is 4, 2. Okay. So if we connect those dots, we're going to get a quadrilateral. It's kind of a weird shape. You should use a ruler. Again, I can't use one on here. Otherwise, it's a touch screen and it really makes messes on my screen. So the first transformation is to rotate it 90 degrees. Okay. And so it says about the origin. Yeah, all of ours are going to be counterclockwise around the origin. And so the rule for that is to do the opposite of Y and then keep X the same. And so we're going to do A prime is going to be -1, 1. B prime will be -2, 2. Again, we're switching the order and changing the sign of the Y value. Okay. C is going to be the opposite of Y, so it's -4, and we're going to keep 5 the same. And then D prime will be -2 and then 4. Okay. So if we plot the 90-degree rotation, okay, we're going to expect something in the second quadrant, and that's what we'll get, okay? And so we go -1 is 1, and that's A prime, and -2 is 2, and that's B prime. -4 is 5, C prime, and then -2 is is 4 as well, sorry. And that's D prime, okay? And so if we connect these together, we should get, you should get a congruent figure. It's kind of ugly. And it should look like you went 90 degrees counterclockwise. And we did. If you connect points A and A prime to the center, to the origin, you'll notice you did go 90 degrees. Okay. Not the cutest figures in the world, but we're kind of going through with it. And again, each of these should be congruent to each other. The next one says, and then take those and translate it using the vector for -2. Okay. And so we know it's going to take our shape right 4 and down 2. Okay. So the blue shape will go right 4 and down 2. I am not counting, but what I will do is I'll put 4 with the X coordinate and -2 with the Y coordinate. And then we'll see what we get for each of these values. So A double prime, if I put the X's together, -1 and 4 together, I'm going to get 3. And if I do 1 and -2 together, I'm going to get -1. So my B prime, our double prime, is going to be, again, I'll put point B with this vector. And so -2 plus 4 is going to be 2. And then 2 and -2 makes 0. C prime, double prime, is going to be -4 plus 4 is 0. 5 and -2 is 3. And then D double prime will be -2 plus 4 is 2. Again, we're putting each point with this vector here. The X coordinate with the X value of the vector, the Y coordinate with the Y coordinate of the vector. and then what component, it's appropriate to say component of the vector. So 4 and -2 is going to be 2. And so when we replot this, we do 3, -1 is A double prime. If we do 2, 0, it's going to be B prime, double prime. If you do 0, 3, it's going to be up here again. This one overlaps. It's not my favorite. And then that's C double prime. And then you do 2, 2. Okay, so if you rotate it, oh no, you're scooching it right 4 and down 2. Yeah, it does go right 4 and down 2. It's just kind of on top of the first figure. And so this would be your final result, your final image. Okay, so sometimes we're just going to take a shape and do 2 transformations in a row and say, hey, look what happens. Okay, and you have to know the formula, so you'll say, can I do each of these? And then sometimes we're actually going to say, can we show that 2 reflections across parallel lines are equivalent to doing a translation? Okay, and that's what we did at the front. And if we do that translation, the distance between those 2 lines that are parallel will be the equivalent to, take double that, you'll get the distance that it actually would have slid, okay, or done translation, pardon me. And then if you reflect it across intersecting lines, it's going to be like you did a rotation. And again, the angle between those 2 lines, if you double it, you'll get the angle of rotation. So in this, most of our stuff will be on either dot paper or it will be on graph paper, because those are the most precise. You know, yes, we can use patty paper, and you know, that does show, it's very helpful for some of these transformations, but mostly we'll use the dot paper as well as the formulaic way using ordered pairs. Thank you very much. Have a good day.